Work.
Looking good.
All right. So, hello, my name is Luke Wagner. I work at Fastly. I'm going to be talking about current plans and technical roadmap for the component model. And this is a draft because it's something that we'll be discussing both at the end of this talk and over the next 2 days, the virtual summit. So it's a good time to give feedback. Also, feel free to follow up offline on Zulip or emails. And the plan is to have a distilled version of this presented at Wasm.io for to share the roadmap more widely. So then, just to start off, I'd start off everyone on the same page. I'd like to briefly recap why we even need the component model in the first place. So one high-level goal that I think we all share is we'd like to see ubiquitous upstream support for WASM in all the major languages, packages, and frameworks, so that WASM just works everywhere, inside, outside the browser. Now we're already off to a great start here. As we can see in this list, lots of languages already have some degree of support for generating core WASM, but to get from some support to a just works developer experience requires more than just time and efforts on the part of each of these languages communities. And that's because the core WebAssembly standard leaves open questions that individual projects need standards-based answers to, since they have to be implemented in a coordinated manner across many distinct projects, including WASM engines, language producer toolchains, and low-level tools like LLVM, libc, and the linker. In particular, we need standards-based answers to questions like, how are WASM modules bundled together into publishable, distributable artifacts? How are WASM modules linked together at runtime with control over the sharing of memory and functions? How do WASM modules communicate values and handles when they don't share memory? How do languages, standard libraries, and packages perform standard I/O with things like files and sockets? How do host embeddings define their own custom I/O APIs that integrate well with standard I/O APIs? How is I/O virtualized in WASM for use cases like polyfilling, adapting, tracing, and proxying? How do WASM modules opt in at the ABI level to new WASM features like multi-memory, Memory64, and WASM GC? How do languages implement their concurrency mechanisms like callbacks, async await, and threads? And finally, how are module instance lifetimes controlled by the host and other WASM modules? And not only that, but when we consider all the places that folks are running WASM today, we need answers that work across a variety of axes, including from whole WASM apps to small WASM plugins in big native apps, from the full kitchen sink of OS capabilities to pure computing environments like database UDFs, from beefy server hardware to tiny microcontrollers, from single language monoliths to highly polyglot composite applications, from isomorphic modules that want to run both inside and outside the browser to specialized modules that don't. Now what we can't do here is try to standardize the least common denominator across all these axes, because that all you'd be able to basically do is build a calculator. Instead, we have to embrace the heterogeneity of the WASM landscape while still finding enough commonality to prevent fragmentation and duplication of effort. So to do that, we've adopted a layered approach where we slice up the problem into two layers. Lower layer is the component model, which provides common answers to all the questions except I/O, while running across all these diverse axes of host environments. And then the upper layer is WASI, which uses the component model to define a collection of standard APIs for all the different kinds of I/O that may or may not exist on a particular host. And you could say this is roughly analogous to a classic microkernel architecture, where the component model is like the always present microkernel, providing foundational primitives, and WASI is like all the OS processes for networking, storage, and graphics that, depending on the device, might not be present. Another reason for the split is that because, like core WebAssembly, the component model doesn't have any built-in I/O, the component model can be implemented natively in the browser alongside core WebAssembly. In contrast, browsers have the very strong opinion that web APIs are the only I/O APIs, and thus WASI would need to be implemented via browser polyfill. And so, in summary, we need the component model to provide standardized answers to questions left open by core WebAssembly in order for us to get upstream support across the software ecosystem so that WASM just works across the diverse set of places that we want to run WASM. So that was the why. Now let's talk about the when. And so as background, WASI Preview 1 started with an initial set of POSIX APIs, and then Preview 2 split out the component model layer to answer a bunch of the questions I just listed, and also added sockets and HTTP to the WASI layer. And any day now, we'll be releasing Preview 3, which extends the component model to answer a bunch of concurrency questions and add async functions, streams, and futures to it. And there's been a metric ton of work from like 20 people across 8 organizations and the community on Preview 3. So a big congratulations and thank you to all involved. Well, we've also done a lot of work on cooperative threads, which I sketched at last year's Plumbers Summit, and my colleague Cy Brand will be talking about in a lot more detail next. Now, we're not quite done yet. There's a bunch of spec tweaks, or a number of spec tweaks and a bunch of toolchain integration work to do. But as soon as that's done, cooperative threads will go out in the next 0.3 minor release, taking advantage of the 2-month release cadence that we set up in 0.2. There's also another small but important addition we need for streams, which is the ability to splice one stream into another without an intermediate copy. It's very important for performance. It just didn't make it into 0.3.0 in time. Now, in 0.3.0, we didn't add any new WASI APIs. We just upgraded the old ones to use new WIT features. But with our concurrent foundations built, we'll resume adding new WASI APIs in 0.3 minor releases, with good next candidates being config, key value, and object stores, crypto, and OpenTelemetry. But likely many more, because with our heterogeneous layered approach to APIs, the more the merrier, and it mostly just comes down to who shows up to the WASI subgroup with multiple interoperable implementations. So then what's next? Well, first, what we're not going to do is a preview 4. Instead, it's time to turn our sights to a component model 1.0. What all goes into 1.0 and when will it be done? Well, that's what the rest of the talk is about. But as a summary and outline for the talk, the plan is to improve the ABI based on feedback we've gotten from the previews, then motivate native browser supports, make it easier to implement the component model, grow the ecosystem, and finally close key expressivity gaps that we've seen in practice. Now, the other half of the story is, of course, getting to a WASI 1.0, but that's dependent on a component model 1.0 and will have to be the subject of a later discussion since this presentation is scoped just to the component model. And one last key part, the whole plan is to maintain stability, which we've been doing since Preview 1, using a combination of semantic versioning, side-by-side implementations, and WASM to WASM adapters. Stability means that you can ship stable Preview 1 releases in production, and indeed a number of us already are. And our intention is to keep the stability story well past 1.0. So while we definitely do want to get to a formal 1.0, you can start using this stuff now. So now let's go through these 5 to-dos, my list, in more detail. So the first to-do is to improve the component model ABI based on the feedback and experience we've gotten since the release of WASI Preview 2. And when I say ABI, I'm referring to the core WASM function type and runtime behavior that correspond to a WIT-defined interface. And a powerful thing about the component model is that its ABI is parameterized by a small set of ABI options that each component gets to pick internally to configure important details like string encoding and multi-memory. Now, as I said earlier, we haven't made a breaking change to the ABI since the release of Preview 2. Preview 3 just added a new async ABI option that components can use to opt in to being more concurrent. But of course, the whole point of these preview releases is to collect real-world feedback that we can learn from and then iterate on before a final 1.0. And indeed, we've gotten some useful feedback. So as a background, if I import a WIT function returning a list of strings, ABI requires the caller to specify a function that we usually call cabireallic. And when the caller calls the imported WIT function and the callee is ready to return its value, the host calls cabireallic to allocate memory for the elements of the list. And then it calls cabireallic again for each strings char buffer in the list, and then copies everything before returning to the caller. And while this works pretty well in practice, the feedback that we've gotten so far is that a generic cabireallic can lead to heap fragmentation over time. Handling large allocation failure gracefully without trapping is hard. Performing one host-to-guest call for each value can be expensive, and it's hard to implement various custom allocation schemes. So to address this feedback, the alternative approach we're considering inverts control flow, so that when the callee returns a value, instead of the host eagerly calling cabireallic and copying each value, the host instead returns lazy values as i32 handles. And then when the caller is ready to copy the value, it calls a special built-in function, passing the destination address as a parameter. And because these built-ins are statically known to the compiler, they can be inlined as if they were instructions. And I think we'll be hearing more about that tomorrow in the summit. And I'll show an example of what this would look like from guest code in a few slides. But for now, I'll just drop a link to component model issue 383 for more details. But with this change, not only do we get to address all the feedback that I just mentioned, but we also get a bunch of other nice to have hop-ons, such as allowing lazy values to be zero copy forwarded between function calls and dropped if they aren't used. The lazy approach also allows the caller to set different ABI options for each value instead of for the whole function call. And it should actually simplify engines by moving some ad hoc string transcoding and auto back pressure policy choices into WASM guest code. It'll also simplify hello world components by removing the call indirect shenanigans that confuse newcomers when they look at their first component. And they're like, what's all this stuff? And lastly, the lazy approach sets us up well for post 1.0 additions like the ability to gather a single list via IOVEC and the ability to have recursive with value types. So a lot of great stuff falls out of this change. But how do we roll out an ABI change while maintaining that all-important stability guarantee I just mentioned? Well, the plan is to add a new lazy ABI option as part of a 0.3 minor release so that producer toolchains can gradually opt in when they're ready. And then when we get to 1.0 and everyone is opted in, we can make the ABI always lazy and just remove the option because it's the only thing. And because the lazy ABI is more general than the eager ABI, we can build an adapter tool that converts any component from eager to lazy. And then once we have an opt-in, we can also fold in a few unrelated but otherwise breaking ABI changes that we've wanted to make for a while now. One is to finally take advantage of WASM multi-value in return types. And another is to include an error context value in every result values error case so that there's always a nice idiomatic way for hosts to attach backtraces and debug info to errors. So when might this happen? Well, the current plan is to start working on this right after closing out the cooperative threads that I mentioned earlier and Sai will be talking about next. Then hopefully it won't take too long because it's a somewhat narrowly scoped change. However, waiting for an LVM release with multi-value return support may end up being the long pole here. Lastly, there's one more orthogonal ABI improvement that I think we need before 1.0, and that is adding a GC ABI option that configures the ABI to use WASM GC allocated memory instead of linear memory, avoiding what would otherwise today be a copy through linear memory. Now, I'm not sure when exactly this work will start, but there's already a great pre-proposal by Nick Fitzgerald in Component Model issue 525 that you can check out if you're interested, and then maybe pitch in. So in a nutshell, those are the ABI improvements that we're planning to make before 1.0. The second to do is to motivate browsers to implement the component model inside their existing JS WASM engines. Now, we don't depend on native browser support since we can already run components in JS engines today using Jcode transpile, which converts a component into equivalent core WASM and JS glue code. And Jcode already makes using WASM from JS a much nicer experience. You just import the component's exports using a JS import statement, and then you can call or await them, and you get to pass and receive normal JS values like strings, arrays, objects, and so on. And since this works today, we don't depend on browsers adding native support, but it'd be a lot cooler if they did. Why? Because there's already some performance gains to be had. At load time, a native implementation could call directly from WASM to browser APIs, skipping the JS glue code. Now, how much real-world speedup there is to be had will obviously vary by workload, but some experiments by Ryan Hunt at Mozilla show that even during doing DOM mutation in a WASM VDOM reconciliation loop can get an almost 2x speedup from direct WASM to browser calls. But there's also a more subtle, powerful reason to want native browser support, which is that browsers are a major gravitational force with massive reach. And when you combine the browser's reach with the component model removing the toolchain dependency on JS, the result should be a major increase in upstream WASM support in languages, packages, and frameworks that would then feed back into a better developer experience for WASM on the web. And fortunately, based on these and other arguments, browsers are starting to seriously consider the component model. The Mozilla folks gave a great presentation at the last in-person WASM CG meeting covering the performance experiments that I just mentioned, and generally making the case why the component model would help make WebAssembly a first-class citizen on the web. And the Chrome V8 team recently created an issue for evaluating the component model and collecting feedback. But of course, the component model is not exactly a tiny feature. I think it's about as small and simple as it can be given all the questions it needs to answer that I listed earlier. But it's a bunch of work to implement, and so some due diligence on the part of the browsers is appropriate. And one way to do this due diligence is to demonstrate growing real-world usage of J-code transpiled components so that the native support is just paving the cow path, which browsers like to do. So to enable this, we're having J-code emit a use J-code no-op string in the JS glue code so that browsers can report it in their existing feature usage telemetry. And for anyone familiar with the history of WebAssembly, this is kind of like how we started with ASM.js, which contained a use ASM no-op string that helped motivate Chrome in particular to optimize ASM.js and then add WebAssembly. So one thing I'll encourage everyone here to do is to use J-code to simplify your WASM web development experience and help us juice those telemetry stats. But this does mean that getting something shipping in browsers is going to take some time. And according to the WebAssembly CG process, we can only get to an official 1.0 if the component model is shipping in at least 2 web VMs. So then that naturally raises the question of, what should we do in the meantime? Which is the context for the last 3 bullets in the to-do list I gave at the beginning. There are valuable things that we can do to take us toward our goal that don't significantly increase the implementation burden on browsers, which is going to be our long pole here. So then, third to do is to make the component model easier to implement. And I think there are roughly 2 big categories of implementations here. We've got producer toolchains compiling source code into components, and WASM runtimes executing components. And for both of these, there's an opportunity to factor out some common implementation work into shared tools. The high-level idea here is to boil WIT down into a pair of traditional C ABIs, one for the guest and one for the host, both expressible as header files. So let's dig into each one, starting with the guest C ABI. So the idea here is to use WIT bindgen to compile WITs into C header files that exactly match the component model ABI. For example, if I have an interface foo containing a function bar, this would turn into an extern C function declaration that uses Clang attributes to mangle the interface name foo along with a version and the choice of WASM32 into the import name of the function bar. And then following the ABI, the WIT string parameter s would be decomposed into a UTF-8 pointer and length parameter, which are then both compiled down to core WASMi32 parameters. Now, string value here is a struct, which today would need to be returned via linear memory. But if we're taking advantage of multi-value returns, we could add some sort of new calling convention, which I've speculatively called WASM multival here, that says to return structs as scalar return values when possible. And what's in this struct? Well, if we're basing the guest C ABI on the lazy ABI, it would be an opaque lazy value index along with the required buffer size. And when the caller figures out where they want to put the string in memory, it would call a lower string built-in function, passing the lazy value index and a destination address. And that's unfortunately all the time I have for this example, but if you want to see a fairly detailed sketch of what the guest C ABI would look like in a preview 2 timeframe, check out component model issue 378, where we were calling it a core WASM build target. Maybe guest C ABI is a bit nicer name. But then zooming out, the point of all this is that now I can compile my source code to a core WASM module as usual, and then feed this core module into a WASM component LD along with the original WIT to wrap it up into a proper component binary. And yet, I don't have to learn a bunch of new componenty things. I'm just calling core WASM imports via C headers, kind of like with Preview 1, which is nice. Now, technically, this guest C ABI will only be able to express a subset of what the component model allows in terms of bundling, linking, and ABI options. However, we can expand the subset over time by adding new built-ins and name bangling options. But if nothing else, the guest C ABI is a great way to help folks get started. And in terms of timing, to minimize churn, we probably want to wait for the lazy ABI to stabilize first. But what's convenient is that the guest C ABI is purely a toolchain convention, which means that it doesn't require any WASM runtime support or a dot release. So that's nice. And that covers the guest C ABI. Now let's switch over to the host C ABI. Now you may be wondering, well, why do we even need a host C ABI? Can't the host just implement the guest C ABI? And the answer goes back to how I was saying that the guest C ABI can only target a subset of the component model. So that means that there are components sitting outside this subset that the host still needs to run, such as compound components produced by WAC that internally contain multiple modules and memories all linked together. But what we can do is leverage core WebAssembly features like multi-memory to smash everything together into a single core module that has the same observable behavior as the original components. And then the interaction with the outside world, with the host, could be governed by a host C ABI that could be generated from WIT by WIT bindgen. And this host CABI would be pretty close to the guest CABI, but have some key differences like passing extra parameters that host functions need, like the memory index and the ABI options to use. But with these, a core WASM runtime could implement this host CABI just like any other core WASM interface. Now, this component smashing tool doesn't exist today, but already Jaco and ArcJet's Gravity, which is built on WAS0, are doing something sort of like it by reusing parts of Wasmtime. So we could pave this cow path by building a proper CLI tool, which I'll tentatively call lower components. And then using lower components and with bindgen, we could more easily add component model support to other core WASM runtimes like Whammer. Now, I'm not sure when exactly we'll have resources to do this, but in general, it seems like a good idea, and I believe we'll get a Bytecode Alliance RFC written up pretty soon about this for more technical discussion. And so then zooming back out, with the CABIs and shared tools, implementing WASI and the component model should be about as easy as WASI Preview 1. And this isn't just a story of there and back again. What we've gained in this process is standardized answers to questions around bundling, linking, virtualization, APIs, concurrency across the heterogeneous landscape of custom and standard I/O, now including sockets and HTTP. So it was worth the trip. Moving on, the fourth to-do for a 1.0 is to grow the ecosystem around the component model. And there's several big ways for us to do that. The first is to write more and better documentation. And of course, we already have an online component model book, which is a great starting point. And there's now also a physical book called Server-Side WebAssembly by Dan Charloni, which is awesome. And congratulations, Dan, for doing such a good job describing the state of the art. But of course, there's still a lot more introductory, tutorial, and reference content that we need to write for each language, runtime, and tool. Another big way to grow the ecosystem is to get stable 0.3 support upstream in all the places. There's already some great progress that you can track on Yosh's awesome WASM components repo on getting WASI P2 and P3 implemented as downstream tools, and in even some great first steps towards upstreaming in LVM, Rust, Tokyo, and Python. But we should do a bunch more. And the last big way to encourage growth is building and improving generalized component tooling that is useful across all programming languages. One such tool is, of course, Jaco, which is not just a component polyfill, but also provides experimental WebIDL imports that allow any language with WIT bindings to call any standard web API without having to deal with any JavaScript. And there's a lot more kinds of tight web integration we should add to Jaco. Another great tool is WAC, which lets you easily plug components together from the command line or using a powerful little linking language to create more sophisticated compositions. But we've all only just scratched the surface of what's possible with WAC, and I think we should take WAC a lot farther. Another important tool is Wackage, which allows publishing and fetching components to and from standard OCI registries. And it works, and some of us are already using it in production, but it'd be great to build higher level tools for discovering and depending on components in OCI registries. And lastly, there's some ongoing work on record and replay debugging that's really exciting and uniquely takes advantage of the shared nothing nature of components. And these are all tools that have already started, but we should start even more. And so that's an overview of some of the things we should do to grow the ecosystem. And the final to-do that I'd like to cover is to close some key expressivity gaps that we felt with our current preview releases. And just as a caveat, the exact names and WIT syntax here is just me speculating, hence the crystal ball emoji. So the first feature, which we've been unofficially calling Stream to UV, is a result of our experience working on WASI HTTP. So in 0.3.0, to fully capture all the concurrent things that can happen while consuming a request or response body, we need a rather complex function type that looks like this. So here we're returning a stream of bytes along with a future that resolves after the stream is done with either the optional trailers or an HTTP error. But we also want the consumer to be able to pass an error back to the producer. And so we have this extra return future as a parameter to the function. But the net result is that it's sort of hard to make sense of this function when you just look at the WIT. So the idea is that instead, we could write this, where our consume body method just returns one stream that produces a sequence of bytes and then a final result that's either the optional trailers or an error code. And then finally, the stream consumer can return a value that flows in the opposite direction back up to the stream producer. And again, I'm speculating on the syntax here, replacing the commas in stream to UV with the keywords then and return to try to make it more readable. But whatever the final syntax, it seems like this generalization of stream would be useful, not just for HTTP, but for any sort of streaming protocol that has state transitions. It's like a lot of them. So that's an additional thing we've been discussing. Another is optional imports, which would allow a component to say, for example, that while it needs to make outgoing HTTP requests, it only optionally requires a web GPU device. And then in the guest C ABI, this optionality would translate into a special feature test function that WASM would need to test before calling any of the real web GPU functions. And this is particularly useful for languages' standard libraries to optionally import everything so they can generate components that run on minimalist host embeddings without having to jettison the whole standard library. The next feature is callbacks, which would, for example, be what you'd need to express the DOM's add event listener method in WITS, which we want to do. Now, there are some very subtle cyclic lifetime hazards that we've learned from our browser experience, but I think we can address them if we have careful scoping rules that ensure that callbacks are GC edges and not GC roots. Another important gap highlighted by web APIs is resource subtyping. For example, we'd like the resource type for DOM nodes to extend the resource type for event targets so that all the event target methods can be called on nodes. Although this sounds like it might open an object-oriented can of worms, this would just be subtyping, not subclassing. And so there'd be no virtual dispatch or complex inheritance stuff for engines to worry about. We also need function subtyping to ease API evolution by allowing WIT interfaces to add function parameters, record fields, and variant cases without having to introduce wholly new functions or declare breaking changes. In theory, this seems simple at the WIT level, but the tricky thing is that we have to think through what happens in all the language bindings so that we can convince ourselves that a WIT level non-breaking change doesn't turn into a source level breaking change. But yeah, we need to do that because evolving WIT interfaces is kind of a pain at the moment. Another important feature is more expressive import and export names. For example, I'd like to be able to import two WASI key value stores, one backed by Redis and another backed by Memcached. And I'd like to include the internal store IDs of my platform in the import names so I can catch and report misconfigurations at deployment time instead of at runtime. And there's a bunch of other ways we can use this feature to improve the developer experience by servicing component dependencies declaratively. Next, getters and setters would allow more idiomatic WIT bindings in many languages. And like constructors and methods, which we already have, getters and setters would just be syntactic sugar for regular functions with special names that the binding generators can recognize. And a map type would allow WIT bindings to produce and consume idiomatic objects, dictionaries, and associative arrays. And indeed, Yortis Prieto is already working on them, so thanks, Yortis. And the last key feature is runtime instantiation. Now, this is something you can do in browsers today using WebAssembly.instantiate. And it's super useful if you want to lazy load code when it's first used, or spawn WASI CLI components as subcommands, as they're called. Or in general, give different components different lifetimes. And you may recall that lifetime is the last open question on my list of questions that need standardized answers. So this seems both pretty useful and also not much extra work for browsers given that they've already implemented something even more powerful in the JavaScript API. So that's a summary of the features we're thinking about adding in a 1.0 timeframe to close expressivity gaps. Of course, we might not get to all of these before 1.0, and there's likely other small things that will get added if we find the need, time, and resources, but it's the current working draft. And so, final summary slide, which I'll kind of leave up for discussions. Summarize the kind of the roadmap here. Talking about, first, of course, ship that 030. It's so close. Just, a few little things to finish up. And then ship cooperative threads and stream splicing in some 0.3 minor releases. Then improve the ABI with laziness, error context, multi-value in some 0.3y later minor release in an opt-in non-breaking way. And then after that, implement the guest CABI. So we have that works like WASI P1 for producer tools experience. And optional imports, which pairs really well with the guest ABI because it kind of gives us a really clean answer for what do I do in my standard libraries if I want to be able to target components of any world and not force everyone to import file system sockets all the time. But still, I want things to just work. Optional imports gives us that answer. And then in some TBD order, while waiting for browsers, but also not blocking. If browsers are ready, like anything that's not ready can be a 1.x, is all those things I just talked about. And then in parallel to all that, should be improving documentation, upstreaming 0.3 stuff everywhere based on our stability, and improving cross-language tooling, especially around Jaco, Whackage, Whack, and record and replay debugging, and hopefully more. And lastly, if we can get it resourced, then the host C ABI. So that's it for me. I'm happy to have some discussion.
Thank you so much, Luke. I can tell folks are being a little bit shy in the Zulu chat. There was not a single message of bike shedding on wit syntax, which is truly astounding.
What?
But folks, please ask your questions in the Zulu chat. If you are on the Zoom and you want to come off mute and ask a question or, have a comment, please do so at this time. I'm going to relay some questions here. So does component model 1.0 mean phase 4?
Yeah, that's what it would mean, and that's where you get that WebVM, two WebVM requirements in the CG, unless we modify the phase requirement, which has been discussed. But at the moment, it's two WebVM requirement. Yep.
And then another question we've got in the Zulip. If someone wanted to contribute to one of these, how would they do it?
One of those, well, there's lots of different projects now, lots of ways to contribute, right? So lots of language tool chains, each with their own, lots of Bytecode Alliance projects, the component model repo if you want to participate in one of those, that, and especially on that last slide in the closing expressivity gaps, the WIT features, component issues. Actually, Bailey just opened one this morning, which is exciting for the more expressive imports and exports. So, component model repo for standardsy stuff and WIT stuff, and all the different Bytecode Alliance projects and yeah, there's so many ways that I can even summarize them all. But I don't know, everyone else, please jump in with more.
A little bit more on that one, I guess. I think you start with a discussion over on one of the issues you linked on your WIT expressive slide. I imagine then if we have a general agreement on that approach, then it would be starting discussion over in WASM tools for a sketch on how we could implement it inside the parser and the changes that would be made there, I think. And for that, I would want alignment with folks like Joel and Alex on those changes and their eyes on it probably before you get too deep in the weeds on implementation. Just starting with the sketch probably is the right move. I'm also asking because, yes, I just put in that PR and now I want to know my next step and, what's the right move.
So there was a question that was maybe a little bit of a joke in the chat by Victor. Does the bike shedding start now, Luke?
I think the best place for a particular scope feature would be in a component model issue where we kind of talk through the syntax. Um, yeah.
Bike shedding with steps. I love it. Um, we have another question. Can those WIT expressive changes happen in parallel?
Oh yeah. Well, there's a lot of parallelism opportunities with all those features mentioned. A lot of it's just prioritize. The best time to do a thing is when you have a use of it yourself, because then you can be the first lead user of it, the dog fooder of it. And so a lot of these things we're scheduling as needed. Each of these is a felt thing, but it's just a matter of when resources are available. So yeah, there's a lot of parallelism opportunities. Sure.
We have another question here from Eric. Seems like parameterized imports would be semantically equivalent to providing some parameterizing module to the imported module. Is the motivation to save the heavyweightness of instantiating a whole nother module?
Let's see. I didn't quite follow the full question there. It's is maybe whoever asked that could ask it in
Yeah, I
more
think Eric's
detail.
on the Zoom.
Yeah, it's hard to say because you say import a lot of times,
Yeah.
but it looks like you're passing strings into modules.
Right.
But you could also provide a second module that has a function that returns a string for that first module to call. Bunch of
Oh
dancing
yeah.
around.
Got it.
So what's
So
the
this is for
motivation?
that generalized import and export names. This, maybe I'll point at it. Oh, yeah, here it is. Uh, this one.
Yep.
Yeah. So the idea is this stuff, what's in purple, is all of it's getting mangled into simply the string name. And you could say at the moment, our string names can either be plain names, which have no standardized meaning, or interface names, which have a very standardized meaning, but you can just have one of them, and it's just that interface name. So you have two kind of faraway options. There's like, I don't know what this is. You're gonna have to figure it out yourself. And this is blessed by WASI or my platform of choice. It has a namespace and a package name and interface name. So what we're saying here is, well, what I want to say is I'm going to tell you what the semantics is, and that's what WASI key value store says. Well, that's defined by WASI. We know what the WASI value store is. But I want a little more metadata that I can find in that import string, such as This is stuff that when I'm deploying, I'm going to say, does my host actually have a store one like this? This attachment, you might call it. Does this exist? Um, and then when I'm code genning my source code bindings, here's a nice programmer identifier that's going to be a global variable that I can use to call key value store methods. So we need, I think, in general, both of these strings. This is like what the programmer gets to use. This is a kebab case thing that gets localized into an identifier, and this is metadata parsed out by the host. But it all goes into the string. So this is just what goes into a name of an import. And this is stuff we would have to put in a separate JSON file or a custom section, but those get lost. Those get split. They come out of sync. Putting it right in the import string like kind of puts it where you want it. And so it gives us the best option to like give us that deployment time error checking.
Okay.
What tends to be lazier runtime errors. So.
Thank you.
Yeah, it's a great question. It's definitely a nuanced topic, and it's going to bear a lot of discussion. It's kind of funny. It's going to be very easy in the runtime. It's just string validated. It's just like the regex gets a few more cases. But how will the tool chains interpret it in all the, for all the build tool chains and how runtimes? That's where all the interesting stuff is. So, yeah.
All right. Well, thank you so much, Luke. That's all the time we have for this session.